So for the sake of not like sliding through a whole bunch of slides, our review from Monday, chirality, you got to deal with RNS and priorities, and that's always fun. So make sure you deal with chirality. We have optical activity. If it's chiral, it's optically active. If it's achiral, it's optically inactive. Ultraviolet spectroscopy, the more conjugated your double bonds, the longer the wavelength. And then IR, we started to look at kind of some nuances within it. And one of them that we ended on was kind of the basics of what IR looks at. It's looking at bonds, and in particular, it's looking at bond dipoles. The larger the dipole, the more the compound will absorb that IR light, meaning we get a more intense signal. So if you go back and think about, because you've all had a chance to review, the intense signals within IR, the carbon-oxygen double bond is one of the most intense and most obvious signals in IR. That one also has a massive dipole, because you have carbon and oxygen. The oxygen-hydrogen is also a very intense signal. Why is it an intense signal? Massive dipole. So if we have large dipoles, we get intense signals. Okay? The converse is also true. If we don't have a large dipole, that signal becomes insanely weak. And there are certain cases where we can end up with IR inactive bonds. Right? And the case that I whipped through really, really quickly at the end of the last class was just saying a carbon-carbon triple bond. Well, if we look at the list that I told you to work with from those videos, that should show up, I always get it wrong, but I think it's about 2150 inverse centimeters. That's where we would expect to see the triple bond show up. But if I go through and add a carbon, well, that might cause the signal to change a little bit, but not a lot. Okay? It might shift around left and right a little bit, but not a huge amount, because I'm not really changing the triple bond. Okay? If I now go through and add in another CH3, well, again, I haven't changed the identity of that bond, but what have I done to the dipole? Okay? There's now no dipole. So while the signal may show up at the same spot, the intensity of that signal goes to virtually zero. And we end up not seeing the triple bond anymore. Okay? This is what's known as IR inactive. Okay? So symmetry plays a very important role when we're looking at IR spectroscopy. Okay? Sort of. It plays a very important role when looking largely at triple bonds. For most other molecules or functional groups, there's enough asymmetry in the functional group that we don't have to worry about it, and it shows up in the IR. Right? The triple bond just happens to be kind of a big red flag that it could potentially disappear from your spectra, okay? From your IR spectra. Okay? So we would hope that there were other methods to be able to distinguish and find the triple bond. Okay? And that's one of the things that we'll talk about a little bit today after we do the quiz. Okay? And that quiz is why you all have that little piece of white paper in front of you. Okay, so everybody should have a little piece of paper. Is anybody missing one? Okay. Perfect timing. You get to enjoy for the quiz. Leave, yeah. Perfect timing. Time to get up and walk out. Okay. So here, starting the quiz, just like we've been doing with every other one, we'll run it at 30 seconds. I'm just going to record for 5 seconds if you go home and watch this. So you'll see the spectra pop up 5 seconds, then will be the next one. Okay? So we'll go ahead and we'll actually questions about the quiz. So 4 spectra. I just want as much information as you can for each of those 4 spectra within 30 seconds. Okay? So 1, 2, 3, 4, dump information about what you see. Okay, starting with number 1. Let's try that again. There's number 1. That's our 30 seconds. That is again our 30 seconds. All right, was our 30 seconds? I went a bit long on that one, sorry. That is our time. So with that, we'll go ahead and hit the next slide. I'm going to pause. IR. Your textbook has a nice little kind of image within IR. So we talked kind of about the theory behind it. It's bond vibration. We have bonds that can disappear. We have bonds that can appear stronger because they're more dipoles. Right? And we end up with a spectrum where we've got percent transmittance on the y-axis, and then we have wave numbers written on the x-axis. Usually about 4,000 down to 1,000. The 1,000 to 500 sometimes gets cut off because it's really hard to interpret. Greater than 4,000 is outside the scope of our class. Right? And so your textbook did a pretty nice job of summarizing what you can expect to find within those regions. So between 4,000 and 2,500, we expect to see hydrogens. Right? And in particular, any atom connected to hydrogen. Right? Be it oxygen, nitrogen, or carbon. Right? And we would expect to see those signals show up in that range. Okay? Then they mention triple bonds, they mention double bonds, and they mention single bond stretches, and then they throw in at the very end bending modes. Bending is a vibration, right? Not easy to interpret. Right? So within our IR, as was discussed in the video, right, and depending on who you end up with as an instructor potentially in the future, right, you may very well see people go through and put a line about there and then cross all of that out. I find that insanely frustrating because you're now ignoring information. Right? So it is okay to do this, however. What is the reason behind it? Why would we ignore that region? It's the fingerprint region. Okay? Lots of useful information in the fingerprint. It can really help us narrow in and identify the compound. However, the human ability to be able to interpret the individual signals within that range now becomes highly suspect. And we really have to trust a computer to go through and analyze that. Okay? What you're expected to do is analyze everything above that, okay, officially. So that's kind of that red line. I would make the argument that there should really be kind of an orange line, okay, or an orange zone. The transition between don't analyze it and analyze it. Okay? Why? We're starting to move closer and closer into the fingerprint region, meaning more and more signals show up in that range. It is easy to get those signals confused. Okay? So when I go through interpret, it's about 1,600 and lower that I ignore at first, and I evaluate everything above 1,600, okay, and come up with some interpretation behind it. Okay? Now how do we do it? Well, the textbook has you think, or has you appear, look at wave numbers. Where does it show up on the x-axis? Then we have something about the intensity of the signal. We also have something about the breadth of the signal. Okay? If I say I have a really large friend, what does that mean to you? What does that mean? He could be tall, but he could also be short and 800 pounds. That would still probably qualify as large, right? Okay. So our definition of those words becomes very questionable because we're making assumptions on those. So when we look at the English language and how these signals are described, okay, intense, very intense, moderate intensity, broad, sharp. Those words lose a lot of meaning because what you're looking at is an image and your interpretation of those words can be different. Right? So the best way to deal with IR is to treat it like you would the little kid toys where you have the shapes. Does the square fit in the circle hole? No? Well, then the square is not a circle. Right? You're saying, well, that's a bit oversimplified. Yes, but that's how you should be looking at IR. If you zero in on every single little peak that you see, you're now overanalyzing it and you run the risk of getting false interpretations out of it. Okay? What IR should be is insanely fast. Okay? Sub 5 seconds, at most. Okay? How do you pick up that speed with recognizing? Practice. Exposure to lots of IR. Right? That's why you have to look at more and more spectra. That's why the textbook shows you a bunch of them within that chapter. Okay? That's why there's the background file that doesn't just say these are the ones you need to memorize. It shows examples of what those things look like. Every time we change an atom, we change the bonds around it. That can change the signal. So we have to be very careful to not overanalyze. Okay? So, what do we see here? You're like just a bunch of friggin' lines. Okay? Look really, really closely. Okay? If we look, we've got 400 in the lower right-hand corner, right? Okay, 400 is pretty close to that 500 we were talking about earlier. And in the upper left, what do we have? Or lower left? 4,000. What are we looking at here? This is an IR spectrum. This is an IR spectrum that lists individual functional groups and says, what do we expect to see for that functional group? Okay? That looks a little bit different than what the textbook showed you here. Okay? It also looks a little bit different than what I've given you. Okay? You can go and find literally volumes of books that just have tables like this. Okay? That is something you could theoretically do. I did it when I was an undergrad, and then somebody told me there were other forms of spectroscopy. I was like, thanks for wasting all my time. Because I spent hours in the library trying to memorize these stupid freaking things. Okay? Yes, it was insanely stupid. Okay? And really, I just wish someone had told me, don't do that. Worry about the next spectra. These should be quick interpretations. Okay? The reason why we need to be quick, we look all the way up at that front top thing here. Well, actually, let's not even do that. Let's just look at 3,000 down. Okay? What I just boxed in, what happened with our functional groups? We have alkanes, alkenes, alkynes, aromatics. Okay? Arguably, even our alcohols start to touch into that. In that exact same region, we get 4 or 5 different functional groups. Don't do functional group analysis. Do bond analysis. Simplify it down as much as possible. Yes, each of those things are different, and you can interpret it. You literally go insane. Okay? Feel free to test it, and then in 10, 15 years, you can come back and talk to me, because you'll probably be teaching OChem, because you literally went insane doing this. Okay? Feel free to connect those dots if you would like. Okay? So, within our regions, what we want to be able to do is look at that spectra and come to as quick an analysis as possible. Your textbook, again, will show you a bunch of different things to evaluate. Okay? What we talked about was 1,400 and lower we should ignore. So we can immediately draw a line. Those two things disappear. Remember how I said 1,600 and lower is a dangerous region? That spectra has one signal for me to evaluate. Okay? Yes, there's a bunch of peaks there, right? Okay, I have a bunch of peaks piling in there. They're all representing the same thing, a CH stretch. How do I know all of those peaks are now grouped as the same thing? Experience, because I've looked at enough spectra, or I looked at that background file where it says the CH stretch looks like this with a bunch of peaks. You need to be reviewing that content as you move through this. Make sense? Okay. So, when solving, IR information, or IR reveals information about bonds, and only a bond. If we go through and look at this list of things that I'm telling you that you should go through and memorize, notice what am I highlighting? Only bonds. I'm giving you the wave numbers, where that signal shows up, and I'm then also saying a rough description of what it looks like. Okay? Those things can vary wildly. Okay? This is where it comes to experience, to looking at these things and seeing when and where they show up. Okay? So those you should absolutely commit to memory. That nails down, at least passing, I would argue, as far as IR spectroscopy goes. If you've got those memorized and can find them, which becomes the next thing. Just regurgitating those numbers is pretty meaningless.
When you say intense, do you mean like...
It's super, no, I mean the signal is larger, which brings in an interesting question. I was kind of waiting to see if anybody would ask that. When we look at this as percent transmittance, our signal usually runs up here, right? Right? What is that signal as shown? Is that intense? No. But that's 100. Isn't 100 intense? If you got 100 in this class, you're telling me you're not going to be intense?
Yes.
You're probably going to be really intense. Why is that not intense? What is the 100 in comparison to? What is the unit? Percent transmittance. That means 100% of the light did absolutely nothing with the molecule. It passed directly through. That's why that is now a 0 intensity. Okay? If we now go through and look at a signal, what happens? How many peaks are shown? 2. But isn't there only one peak? Isn't that the only one peak? Okay. IR is read upside down-ish. Okay. Our peaks are here. Okay. Between those two, the first one is more intense than the second. Is the second one low intensity or medium intensity? I literally have no way to answer that question. Okay. That entirely depends on the situation and what you're looking at within the spectrum. Okay? So be careful over analyzing those intensities. It's dangerous. Okay? And it is also very easy to do. Okay? IR should be almost a gut instinct. This is what it is. Okay? After that, we have what I would call my BA list. These can be extra useful because they can help us really nail down that last 30%. This can actually get us to functional group information. Notice we do have some repeats. The OH shows up on this list and on the previous one. And here it says 33 to 35, intense and broad. What does it show here? 27 to 32. It's still an OH. Why is it different? I put that OH near a carbonyl. That caused the bond to change its vibration, and we see a significant weakening of the signal of the energy of that bond. Okay. Why would that bond get weaker when I move it near a carbonyl?
This affects the dipole.
That's intensity. Why is that red bond now weaker than if I had just show it in colors, I guess. I have no idea how to answer that question. We just took an exam on structure, and within that structure I said you needed to know particular functional groups. What is the functional group? COH? Alcohol. What is the functional group? Carbonyl OH. Carboxylic acid. What do acids do? Donate hydrogen, or donate H+. What does that mean? That hydrogen is now acidic. Why is that hydrogen acidic? Because that red bond is weaker. Why is it weaker? An organic chemist's favorite 9-letter word. Resonance. Okay? It all stacks. We have to keep constantly referring back to it. Okay? The rest of these do similar things. It's elaborating on information that was already provided, okay? Or just kind of nuancing out some special details. Okay? Kind of makes sense? Okay. 10 seconds. What do you see? There's our 10 seconds. I have a CH. Okay, it's falling in that range. The question now is what kind of CH? Okay. I can draw down. Those are less than 3,000, which makes them SP3. That signal here shows up about 1,700, which means that is carbonyl. There we go. Carbonyl, carbonyl, I don't really care. Right? Everybody says it differently. Somebody calls it a carbonyl. I kind of laugh at that one, but okay. It can be very difficult to see that line. So what I would recommend you do, and it's going to be really, I can do it on my screen. That's not going to be helpful. Okay, on an exam, I will try and blow those numbers up. On the ACS, they may not. Okay, on your homework, they may not. Okay, so it might be helpful to be able to see exactly where that is, because that's a big gap and a big difference. CHSP3 versus CHSP2. How can you ensure you've got it right? Well, just draw a dotted line. Yeah, because everybody can draw a dotted line or even a straight line that's actually straight. Okay? Get a piece of paper, align it with the bottom axis. That is now straight. We have a perpendicular line using the other edge. We line it up with my 3,000. Where are those peaks? They're visible, so they are by definition under 3,000. That makes it CHSP3. I don't have to pull out any fancy tools. I just take another sheet of paper that I have handy. Next one, 5 seconds. That was 5 seconds. We get an OH. We get our CHSP3s. And then I would ignore all of that. Okay? At 1,500 to, what do we say, 1,400? Yeah. Are there some peaks in there? Yeah, I would ignore those. Okay? Not worth the effort to try and nail those down. Okay? 5 seconds. I believe that was 5 seconds. There's my 3,000 line. Okay. For those of you that don't believe me, again, it doesn't work quite as well because it's a projector, but we hold our paper right on that line. There's our 3,000. Okay. Those peaks, right? Clearly less than 3,000, but
More than 3,000.
that other peak is more than 3,000. What do I have in that one signal? CHSP2 and CHSP3. Both signals are present. Does that overall look that much different than just a CHSP3? No. That line on 3,000 is a hard line. Find it, use it. Right? After that, I have a CHSP2, which means I have an sp2 carbon, which means I more than likely have a carbon-carbon double bond. So now I could fish down lower. Whoops, too low on my screen. I've got a peak there sitting at about 1,600. That's probably a carbon-carbon double bond. Okay? 1,600 also usually is a little bit low for a carbon-carbon double bond. It's low because there's resonance and the double bond has been weakened. It would get weakened because that carbon-carbon double bond is showing up in an aromatic benzene. What evidence do I have? I have another sequence of peaks a little bit lower down. That, in conjunction, helps me to say that more than likely I have an aromatic ring. Okay? Notice again, I put a question mark there. I don't want to put overweight on that. I'm now dancing with the fingerprint region.
So does the aromatic ring have to have that second peak behind it?
It doesn't have to.
Okay.
Another 5 seconds. I lied, I don't want to wait. What do we see? Okay. I immediately see the carbonyl at 1,700. I've got some CH over here. In the previous ones, where was that distance between that peak and the baseline, or the bottom? Those things were really close, right? So I could draw a reasonable straight line, and you're like, that wasn't that big a deal. That's kind of far away. Okay, that's probably not easy to do, and that, unfortunately, is probably larger than my, yeah, it's larger than my paper even. Okay, on an exam, it's not larger than your paper because your exam is printed on paper. Okay, so you could use the piece of paper to line that up. Make sense? I'm going to take a stab that we have CHSP3 and CHSP2. Okay, that's going to come from experience looking at this. Those of you that printed out the slides could line up the paper and be like, see if Mike was right, or you could prove that I was wrong. Right? But that's the analysis that you should go through. Make sense? Okay. So, mass spec. What is mass spec? Blow it up. Okay. That is literally what we're doing with mass spec. We take our molecule, we go, I don't like you, organic chemistry, die. Okay. And it blows apart. We then evaluate all those pieces. So those of you that have been in, say, CSI, interested in forensic potential science, and are concerned about how you could evaluate the different pieces of a crime scene and put those back to draw a conclusion, that is mass spec. Okay? Except on a really tiny scale. Okay? We take our molecule, we fire a bunch of stuff at it, and it destroys things. What it's going to destroy is removing a single electron. Okay? Depending where that electron is located in the molecule may fall apart into pieces. Right? Just like if I took a bomb, right, and placed it inside, I don't know, a car versus inside a tank, I'm going to see different results. Right? The tank is kind of designed to withstand explosions. A car, not so much. Okay? Which means I'm going to see different results coming out of that. So the strength of the thing that I'm trying to destroy can affect the signals that I see. Right? So once I've blown it up into a bunch of tiny little pieces, I then send those pieces through a system that separates, similar to the concept of column chromatography for those of you in the lab. For those of you not in the lab, it separates. That's all you need. Okay? We then have a detector at the end that just counts. Something hit me. Something hit me again. Oh crap, a lot of things are hitting me at the exact same instant. Okay? What it corresponds or correlates those hits to is now the number of particles of a particular mass. So that when we go through and evaluate a mass spec, what we're looking at is the mass of the individual particles. So here's my ionization beam, there's my compound, I fire an electron at it. If the electron belonged to, say, the carbon atom, well, I didn't break any of the bonds. But the molecule is now charged because I removed an electron. Okay? That is the original mass of the structure. Okay? What if I fire the electron at it and it happens to hit the electron in the bond between carbon and hydrogen? Well, that bond now breaks. It's going to break in such a way that I generate the most stable pieces. Okay? If I fire it and it happens to hit the carbon-carbon bond, well then that bond breaks. Again, generating the most stable pieces. Okay? In all of this, what we're talking about is the stability of the pieces coming out of it. Okay? So we're looking at the stability of a carbocation or a radical. Okay? Because there's too many things on that slide, let's go ahead and clean that up. Let's just look at the radical, because radicals are easy, or sorry, not the radical, the cation. Cations are easier to understand. Why are each of those structures unstable? They're all charged. They're missing their octet. Okay? So they want more electrons. What would make them more stable? Being near more electrons, right? Right? So let's take a look at that carbon. What is close to that first carbon? Closest thing. Hydrogen is not the closest thing. A plus is not really a thing. That's actually a lack of things. We could start to get into orbitals. The bond. Okay? Yes, that bond goes to a hydrogen, but there's a bond that's closer than the hydrogen. How many electrons are in that bond? 2. And the next bond? And the next bond? 2. So I have a total of how many electrons around that carbon? 6. Okay, let's do the same argument with the next one. How many electrons in that bond? That one? This isn't looking so hot. Next one. Okay, well, Mike's theory sucks. Let's try again. I like the yeah, your theory was bad. Thank you. I've only been doing this a couple years. Give me a break. What's the difference between each of those structures? Carbons versus hydrogens. Okay, well, so let's go back to our starting one. How many electrons do you want to tell me hydrogen has? One. I'll accept that. Okay, we can run into arguments about that, but let's remember that we said one. So for that first one, how many electrons are around that carbon then? 3. Because the other electrons it owned, it brought in. Okay, how about the next one? Well, each hydrogen brings in 1. What is the difference between carbon and hydrogen? Carbon has more electrons. How many electrons do we want to say carbon has? All except 4. Where do we get the 4 and the 1 from? Valence electrons. So there's 6 around the next one. Okay. How about the next one down? Carbon has 4. Next carbon has 4. That would be 8. Plus 1. 9. And the next one? Thank you for not making me count that out. Okay. Do we see a difference? Yes. What does that difference help us think about now? Which of those do we think might be more stable? Why would the bottom one become more stable? It has more electrons around it. That's it. There's no resonance here because we don't have pi electrons. We haven't addressed that at all. Okay? There's no lone pairs. We're literally talking about the electrons just nearby. Okay? We said the carbocation was unstable because it was missing electrons. There's 12 electrons around this bottom one. There's 3 around the top one. The bottom one is more stable. Guess what? You're right. Okay, for those of you that were there for that lecture, sparkly stuff falling. Good job. Okay? What happens if we move to a radical? What makes the radical unstable? It only has 1 electron. What does it want to be more stable? Another electron. What's the relationship between radicals and carbocations? They're both unstable for the exact same reason. Which means which is most stable? The bottom one. I want to be able to name these things because now I know there's a difference in energy. How could I name them? Well, the top one has no carbons. Mathematically, that would equate to... Seriously? Okay, let's try the bottom one. The bottom one has 3 carbons. Mathematically, that would equate to 3. Okay. 3 for 3 carbons. The top one has 0 carbons, so mathematically that would be 0. So I could go through and name these 0 carbons, 1 carbon, 2 carbon, 3 carbon. Okay. 4 carbon, 5 carbon, 6. Okay. We can't go beyond that. So what can we go through and do? Because that's not fancy enough. We go through and we can refer to these as tertiary, secondary, primary. Okay. The one with the degree is now saying I have 1 carbon connected to my species or my reactive site. 3 means 3 carbons connected. Okay? I personally don't like the name we give to the top one. The top one we actually call methyl. Where's the number system? I prefer zeroary because it's 0. Okay? Your textbook will reference it. If you write zeroary, I might even give you bonus points. Okay? Try and propagate the horrible soundingness of that. Okay? How confident are you guys in this right now? You guys actually kind of laughed a little bit. Right? Should we quiz you on it? Too bad. What happens now? So now we're looking at the far right of the screen. Those would all be anions because they're negatively charged. One of the mistakes that potentially happened in the first exam looking at structure you are responsible for recognizing that if you have a negative charge and that carbon only shows 6 electrons, what else is present? A lone pair. Okay? Now we've extra talked about that, you need to know that's there. What makes each of those anions reactive or unstable? Say unstable. They have an octet though, right? So why are you saying too many electrons? What makes them unstable? The charge. The formal charge is negatively charged. Does carbon want to be negative? No, no atoms want to be negative. That's technically a bad thing. Okay? So the thing that makes these structures bad is the negative charge. To make them more happy, what should we do? Take away electrons. I'm not removing any bonds, but what am I doing?
A new bond?
No, we could potentially form a new bond, but then they could all form a new bond. That doesn't differentiate them as they are. How many electrons are on the bottom one? Carbon, carbon, carbon. I'll accept that because the lone pair, 14. How about the top? 5. Which of those is more unstable? The bottom one, because what have I done? I put more electrons into the same space. Anions flip on you. Why? Because anions are reactive because they have negatives. To make them more stable, don't put them near more negatives. That's the wrong direction. Put them near as few negatives as possible. What we end up seeing is the most stable now flips on us. Okay? Neat. At least I think so. Where does this come back to mass spec? Mass spec says I blow things up by removing an electron. I generate radicals and cations. Okay? I then evaluate all of those pieces. Okay? So what are the pieces that I could potentially get out of mass spec? This is what I do. M+. This is all I did was remove an electron, so the mass of the particle stays exactly the same. It is the peak furthest to the right because, well, it's representing mass. Okay? It is also the tallest peak furthest to the right. Okay? And everybody runs into issues with that. Okay? So the peak furthest to the right, look within 3 units of that, plus or minus. Just 3 mass units. Okay? Find the tallest peak there. That, typically, 95% of the time-ish, is your molecular ion peak. That is now the molecular weight of your compound. You have information. You could use your unsaturation calculation, which I told you that you should deal with because I'm horrible at that calculation. But if you do that, you can then determine if there's double bonds or rings that are present. Awesome. That gets me some structural information. After that, we have to now look at the actual mass value. If that value itself is odd, okay, and I don't mean it looks weird, literally the number is odd, we have nitrogen. That's it. So I see a 91, nitrogen's present in the molecule. Okay? And it has to do with the bonding patterns that change when we move from carbon to nitrogen. Okay? M+2. So now I'm saying I took my tallest peak, furthest to the right, and I add 2 units to it. Do I see another peak? If that other peak is roughly the same height as my M+, then I know bromine's present. Why would I have an extra peak at 2 units out? This is mass spec. Mass is dependent on protons and neutrons. The identity of our elements are our protons, but we could change the number of neutrons to get a different isotope. Some elements have very common isotopes. Hydrogen is not one of them. Okay, we have protium and deuterium for hydrogen. Protium makes up 99% of all hydrogen. Deuterium makes up less than 1%. There's also tritium. Okay? So if I looked at the mass, I would only expect to see a contribution from hydrogen, not deuterium. Bromine's a bit odd, because if I look at bromine, it turns out bromine has 2 very common isotopes, 79, and 81. Even though when we look at the mass of bromine, it's 79.9. Because if I average 79 and 81, guess what I get? Darn close to 80. Okay? Those two isotopes are found in all bromine, which means if I have a compound that has bromine in it, half of those bromine atoms will have a mass of 79, the other half will have a mass of 81. That's why I see a second peak. I could do the same thing for chlorine, though it gets a little bit difficult, because now it's not 1 to 1, it's technically 3 to 1. Okay? The molecular ion is 3 times as tall as the other one. I could do the same thing for hydrogen. I have one peak that is 99 times larger than 1. How many people can easily look at 2 peaks and say, yep, that's 99 times larger? Yeah, that's why we don't do it. Okay? That's why we do it for bromine and why we do it for chlorine, and that's it. What are we done? 45, right? Yeah, okay. The last one we can look for is iodine. Super rare, but it can pop in there. It's one of our common organic molecule or atoms that we can use. The reason why it doesn't show up very often is because it's insanely obvious when it's there. Iodine has a mass of 127. So if your mass, when you look at your mass spec, is huge, it's probably because iodine is present. Right? You will likely also see a peak at 127 because an iodine cation isn't all that unstable. So we'll see a peak sitting there for it. Okay? So, after that, if we look at an example mass spec here, right, it would have been nice if the textbook or the place where I stole this from hadn't gone all the way out to 160. Why do we not need to go out to 160? There's no peaks there. Okay, so the peak furthest to the right, okay, within 3 units, the tallest peak. Okay? So I would look at the x-axis and see where that tallest peak was. Okay? Can anybody see the numbers or the tick marks telling me where that is? No. So what did we do? We told you where it was, 86. Same deal for all these other peaks. We're telling you where that tallest peak is. Okay? In the analysis we just talked about, the only thing I mentioned was 86. What happens to the rest of the mass spec? Ignore it. Don't even need to worry about it. Okay? Unless, that is, you want to be kind of a bomb expert or forensic scientist, where you would potentially need to study the explosion patterns of these molecules. In which case, you might want to start evaluating where those things are coming from. Okay? So, I'm not going to get into that. If you care, you can talk to me after class and we can start looking at how those things break apart. It's not a big deal. But what I do want to get at is the last little bit of information out of this. Okay, 86. Okay. All I'm given is this spectra. Okay, but I'm going to add some extra information in there. When I look at the IR, I see no evidence of an oxygen. Okay. So now, oh, hi, how you doing? Thanks for coming through the door. Yeah, that worked out pretty well because the door actually opened. Damn, people turned. Ha. Okay. What happens? Thank you. I appreciate that. Okay. We use our mass spec. We trolled to no oxygen. I had to tell you that because mass spec doesn't tell you that. We know the molecular ion is 86. Is there bromine? No. Is there chlorine? No. Is there nitrogen? No. So all of the stuff I've told you already isn't there. Okay? The lack of information is information. Write that down. Okay? What can we do with the rest of this? Okay? Well, this is OChem. If it's not oxygen, nitrogen, or any of the halogens, the rest of that mass is carbon and hydrogen. So my compound could be H86. Everybody laughs at that. That's mean. Okay. That doesn't make sense because hydrogen can only form one bond. So I couldn't possibly have 86 hydrogens connected to each other. So I have carbons in there. Okay. So I'll account for the most amount of carbons I could have in my compound. Because I know carbon weighs 12, I can take 86 divided by 12. For those of you that don't want to bring calculators, that's cool. Just know your factors or your multiples of 12. For those of you that don't know your multiples of 12, bring a calculator and somebody tell me that answer. 7? All I need is the first number. What is 7 times 12? 84. Okay, that's all I really needed. So what we're saying is I have 7 carbons. Okay, the remaining mass has to be hydrogen. So I'm saying I have C7H2.
No, doesn't work.
That absolutely works. Don't no, it didn't work. Yeah, that works. Okay. Would it look awful? Yes, I agree. I agree. Okay. So what does that mean? I have too many carbons. So what could I do? Make it C6. But then I've lost 12 mass. Add that in as hydrogens, and I've got H14. I could continue to do this almost indefinitely. C5H26, C4H38. Okay. And eventually we'd probably get into that, well, there's 96 hydrogens, that doesn't make sense. Where's that line where it stops making sense? Conveniently right here. A fully saturated carbon structure, I keep doing that. CN, oh, you don't die on me now. CnH2n plus 2. So in this case, if n is 6, the most hydrogens I could have would be 14. Ooh, that's my line. Okay. So my possible formulas for this are C7H2 or C6H14. Right? Because someone was kind enough to actually draw in the answer, or walk back out the door so we could magically have that appear again. How many carbons in the structure? 6. How many hydrogens? 14. Hallelujah, it matches. Okay? Knowing the rest of that is now discussing how that molecule breaks apart. That would be known as your fragmentation patterns. That's much more advanced. If you want to look at that, you can. The textbook talks about it a little bit, but they also try and leave it alone because that is a whole new topic in and of itself. Okay? So, to my favorite. In only 20 minutes, we've only got like 10 slides left, so not bad. NMR, okay? And ignore that MS statement up there, because now we're just looking at NMR. Okay? NMR, nuclear magnetic resonance. So we're looking at a nucleus, and we're making the statement that that nucleus is now magnetic. Turns out it is. Okay? Has anybody taken like a copper wire and wound it up into a tight coil and then attached a battery to it? What happens to the coil? It becomes magnetic. Okay? Why is it becoming magnetic? We have current turning. If we have a charge that loops on itself, guess what we generate? A magnet. Well, what is a nucleus? Charge. That is spinning. Guess what we just made? A magnet. Okay? So what I'm doing in NMR is I'm now studying the nuclei of particular atoms. Okay? The nucleus must be magnetic, okay? Which brings in kind of an issue within this. Not all nuclei are magnetic. Hydrogen happens to be one that is immediately magnetic right out of the gate, which is awesome because hydrogen, H1, has a massive abundance. So if I look at a sample, an organic compound, every single hydrogen in there is detectable by the instrument. Okay. What is the other NMR I told you to look at? Carbon NMR. What is the most common isotope for carbon? Carbon-12. Guess what carbon-12 is not? Magnetic. Which means if I look at a spectrum for carbon, I'm not studying carbon-12, I'm studying carbon-13. So when you see the notation of, say, HNMR, you notice you see the 1 there? That's an R. That 1 is because that is the nuclear mass of hydrogen. You mean atomic notation that at very least was taught in 130? Yes. When we look at carbon-13, or carbon NMR, you almost always see the 13 written first. Why? Because that's the one that's magnetic. Okay? Not all atoms have magnetic nuclei. The larger issue then comes into the amount. Carbon-13, or hydrogen NMR, you can run a good one in about 5 minutes. Carbon, you need an hour, 2 hours. Why? There's fewer atoms that are magnetic, which means I have to run the sample for longer. I have to do multiple trials and add those trials to get enough signal to detect it away from the noise of the background. So carbon NMR takes a lot longer than hydrogen NMR. There are other isotopes that have similar issues. Okay? We have to have that magnetic system. Okay? So what happens? We take our sample and we drop it in a giant magnet. That giant magnet now has its own magnetic field. Our nuclei can either align with the magnetic field up or they can align against it. That means there's 2 possible energy states. Okay? So we get spin states with our nuclei. That's what's happening with our magnets. Okay? What we can then do is say, well, what else is around that magnet? Okay? If I wrapped, this is totally radiation so it doesn't work, but whatever. Let's say I take my magnet and I put a lead blanket around it. Okay? Would I be able to detect the magneticness? No. That's probably not true, but you get where I'm going, right? We have a shield, okay, that protects it. Well, guess what electrons do? The exact same thing. The electrons around your atom will shield that nucleus from the effects of the magnetic field. Okay? Which means, based on the signal that I get out, I can correlate the location of where that hydrogen is. Is it next to an atom that's taking electrons away from it? Is it next to an atom that's giving it electrons? That's going to change where it shows up in the spectrum. All right, the next layer on top of this. Hydrogen's a magnet. In an individual sample, how many hydrogens are there? Probably more than one, right? What if those two get close to each other? Will those 2 magnets affect each other? Yes. So not only do I see a signal due to just electrons being around the magnet, but the magnets being near other magnets will have an effect on what I see. Okay? That is what NMR is looking at, and we correlate the signals that come out of that into massive structural conclusions. Okay? That is why it's awesome. Okay? So there's our electrons hiding it. A rough idea of your spectrometer. We have a magnet. We drop our sample in. Okay? We have to use an RF transmitter. We use radio frequencies to mess with the magnets. That's actually how we're detecting the hydrogens. Okay? That then comes out and prints out into a signal. Okay? That looks relatively simple, so let's take a look at a real instrument. Okay? The NMR is that giant white thing in the middle there. I mean, the instrument is that big? Yes. You need stairs to climb to the top to put your sample in. That must mean you put in a really big sample. No, it's about the size of this pen. That's what you're putting into it. Okay? Why do you need a magnet so big? Well, some samples are so complicated that we're trying to differentiate a lot of stuff. So we need a bigger magnet to help us make those differences more obvious. This one happens to be an 850 megahertz magnet. The standard in the industry, I think, is 300. It's starting to increase to become 400 or 500 because we can get more information out of it. Why would I not only use an 850 if I get better information? That's really expensive. And that's not just the instrument. I have to have a magnet that's that strong. Okay? How strong is that magnet? See this red line right here? That nice flat one? Okay? That line means don't cross if you have any metal on your person. That next one means you will die. Okay? Because whatever metal is on your person, as soon as you hit that line, is now busting out of wherever it's being held to hit the magnet. Okay? So if you've seen videos or you work in a medical facility with MRIs. MRIs is the exact same process. You can look up like YouTube videos of people being like, oh, I'm just going to carry this cylinder of gas through this room. Cylinders of gas are magnetic and will usually go flying through the room and come slamming into the instrument and usually destroy it. That usually results in the end of that person's job because an MRI is mildly expensive. Yeah, just mildly. Okay? So for those of you wondering why we don't have one here, it's because it's expensive. Okay? And it's not just the instrument. I have to keep that magnet alive. Okay? To get a magnet that strong, what else do I need to do? Electricity is part of it. Any physicists? Cold. Okay. The colder my sample is, the better magnetic field I can get. So I have to get my magnet super cold. Well, why is it not in a refrigerator? Okay. What's around that magnet right now is increasing layers, starting with, I believe, liquid helium, moving up to liquid nitrogen. Okay. Liquid helium boils at about 4 Kelvin. That's really cold. Okay. Really expensive. To run these instruments, you have to have those cryogens to keep it running. Okay. Which means you can get hired to be the person to fill up the instrument. Okay. You just got to pour the really cold stuff in. Not that big a deal as long as you don't pour the wrong liquid into the wrong hole. Okay. That usually causes big issues. I've got stories about that one too. Okay. I didn't do it. Experimental considerations. Okay. What we're looking at is our nuclei being shielded. Okay. So it is now more shielded or less shielded. More or less shielded than what? Okay. If you don't have a standard to compare to or a way to normalize the data, you can't draw conclusions. Okay? So every NMR sample has a standard added to it. That standard is typically TMS. It's tetramethylsilane. Okay? That is then set to be the 0 value on your NMR. Okay? So you may see a peak at 0 in some of your spectra. That is TMS. That's not your compound. That's the standard. Okay? The next part. Okay? Our organic protons are going to absorb to the left of that because they are less shielded. Left? Where's my spectra? I always get them backwards. My left and rights, that is. 0. Hey, I got it right. To the left of that. Okay? Because they would be less shielded. Okay? Tetramethylsilane is massively shielded. Okay? Less shielded can be known as deshielded. It can also be known as downfield. You may see those words. I always screw them up. Okay, so don't stress about that. The sample has to tumble and move. Why does the sample have to tumble and move? Does anybody? No, nobody has one. If you build a chair, right, and we looked at the hydrogens on a single carbon, we had one that was axial and one was that equatorial, right? Were they the same? No, they had different energies. Which means if we ran them in an NMR, what would happen? You'd see 2 different signals for each of those hydrogens. Okay? If our sample's allowed to tumble and move, guess what happens to those 2 hydrogens? They become the same thing. Okay? So our samples need to tumble and move to minimize issues with equivalencies in hydrogens. Okay? So this means we can only test a liquid because a solid can't tumble and move. Okay, well, that becomes problematic because a lot of our samples are solid. So how can I run a NMR on a solid? I could make it a liquid, but then that's too hot, or I could add a liquid. I could add a solvent. That is exactly what we go through and do. But what's the problem with adding a solvent? What are we likely also adding? Hydrogens and carbons, which would then overwhelm our signal because the solvent is in there in such a high concentration that I would never be able to detect my sample. Okay? So when I pick a solvent, the solvent cannot have hydrogens or carbons in it. Well, carbons becomes a little bit less important because we're looking at carbon-13. Okay. Chloroform ends up being the solvent that's typically used. Okay. The other one is dimethyl sulfoxide. If we know the structure of chloroform, notice I said if. You don't, that's okay. Uh-oh. Anybody know the structure of chloroform? No, good. I think that's the structure of chloroform. We're just going to accept it. Let's just pretend that's the structure of chloroform, whether it is or not. Okay. We have a bunch of hydrogens. That would destroy my signal. How can I make sure I don't have hydrogens? Use a different solvent. No. Still has to be chloroform. Replace the hydrogens with something that isn't magnetic. You mean like deuterium? Yes. Deuterium has all the properties of hydrogen except it has that extra neutron. That extra neutron makes the nucleus non-magnetic, which means doesn't show up. Cool. The problem is hydrogens are found everywhere, and hydrogens will exchange with the deuterium, and we almost always see a signal for chloroform in our spectra. But the amount of it is very, very, very small.
You're off.
It's 3 hydrogens, or 1 hydrogen and 3 chlorines?
Yeah.
It's on the very next step, right?
Close, but no.
So due to our hydrogen exchange, we always deuterate, so CdCl3. Okay. We will see a signal in the hydrogen NMR at 7.26. It's a single peak. Or 77.2. 77.2 hydrogen? What is 77.2? Starts with a C. It's the carbon NMR. Okay. So chloroform has the possibility of showing up in your hydrogen NMR at 7.26 or your carbon NMR at 77.2. It shows up as a T. What is T? Triplet. 3 peaks. Dimethyl sulfoxide is a lot more complicated. We actually need 6 deuterium. So you usually see that written as D6 DMSO. If we have it in hydrogen NMR, it shows up at 2.50. It shows up as a pentet, right? 5 peaks within the signal. If it shows up in the other one, carbon NMR, 39.5 as a heptet. Right? That's just general information. Don't stress about memorizing that information. So now we move into the next part, which is the fun part in NMR. What do we do with this? Okay? Well, there's really 4 big pieces of things you can get out of an NMR. The number of signals, the chemical shift, the integration, and the multiplicity. Okay? The number of signals. How many groups of peaks do you see? Okay? Each group corresponds to a unique type of hydrogen or carbon. Okay? So just looking and counting how many peaks you see or how many signals tells you some information about your structure. Okay? So when I had you go through and just say, what do you see with each of those things? The number of signals is an easy thing to write down that could allow you to draw massive conclusions, particularly on a multiple choice test. This is why I want you to do it. Okay? Chemical shift. Well, the chemical shift is where it shows up. Where does that peak show up on your x-axis? Okay, well, it shows up on the x-axis dependent on the things that are around it. Okay? The local chemical environment. Okay? So that's saying what is bonded to the hydrogen or the carbon. Integration, that's the area underneath the curve. And much like mass spec, okay, we will see that if a hydrogen shows up at, say, 1, and I have another hydrogen just like it, well, it also shows up in the spectra, but it shows up at the exact same space, which means that signal grows. So the integration gives you information about the amount of hydrogens. Notice in that statement, did I say anything about the number of carbons? No. That's because when we're looking at simple NMR, integration does not show up in carbon NMR. Okay, we do not evaluate it. It's only for hydrogen. And even then, for hydrogen, it gives us a ratio, roughly equivalent to the empirical formula of hydrogen in our compound. Not the exact number, but the ratio. The last one is multiplicity, also known as splitting. I oscillate back and forth between those. I'm trying to stick to multiplicity as a term because it's less confusing. This gives us information about how many magnets are near it. Okay? So that gives us an idea of the neighbors. Almost everybody jumps into the neighbors because when you watch somebody solve, that's what they do. Okay? That's because they spent 50 hours dealing with the number of signals, chemical shift, and integration, that they've now internalized all of those questions. And they're now jumping to the hardest part because they've already done the rest of the work. You haven't done that work. Do it first. Okay? The other part on why you should do it first, is there information in that area? Yes. Okay? It may not guarantee you an answer, but if you're on a multiple choice test, you can probably narrow your answer choices down with the top 3. Those top 3 things can happen in under 30 seconds. This last one can take minutes. Okay? So it makes sense to use the easiest stuff first. Okay? The number of unique atoms. So the rough approximation for your number of signals, if you build a model of any structure you want, okay, point to an atom, particularly hydrogen, close your eyes, spin, flip, rotate, turn it around, do whatever you want to the molecule, stomp on it was another suggestion. And when you open up your eyes, can you point to the exact atom? Or are you going to get it confused with another one? Right? If you get it confused with another one, then those atoms, however many of them there are all chemically identical. Okay? They may be connected to the same carbon, they may be connected to different carbons, okay? But they are chemically identical, which means they get one signal. If you can tell it apart from everything else, then that one is unique from all the other hydrogens. That's its own signal, separate from the others. Okay? Because it's always fun to end on a horribly hard and ridiculous topic. I've had a couple of students ask questions about some other words. You can encounter some sub-classifications within this. Okay? As far as I'm concerned, everything above this subclass, so that is what you need to do. This is so teachers can feel intelligent about talking about NMR. Okay? Because I don't feel intelligent ever about talking about NMR. I typically skip these words. Okay? Homotopic, if I look at 2 hydrogens, I can call them homotopic. Okay? They have the same signal. I could look at 2 carbon or 2 atoms, and I could identify them as enantiotopic. They'll have the same signal. If I look at 2 atoms and I can define them as diastereotopic, then those 2 atoms are unique. They have different signals. Okay? Where this comes into play is if we look at a structure. So let's pick propane. I want to look at this hydrogen versus this hydrogen. Okay? So in the reference on distinguishing the relationship between those, I'm going to make one of those X. Okay, in one structure. In the other structure, I'm going to make the other one X. What is the relationship between those 2 structures? Well, we just changed wedge to dash. Careful. CH3, CH3. What is the relationship between those 2 structures? They're the same. They're identical. What does that mean? The hydrogens that I subbed out with X are homotopic. Like, why would you do that? I agree. Just stomp on the molecule. Okay. What is an enantiotopic? Okay. Well, an enantiotopic, I now go through and take a look at this structure. And I want to decide between these 2 hydrogens. So I'm going to make one X, and the other one I'll make X. What is the relationship now between these 2 structures? Just for the record, there's another H back there. These two structures are, oh, son of a, oh, never mind. I think if I did this right, they're enantiomers, which I could easily have screwed up. Remember, I don't feel intelligent on this. Right? I could reference them as being enantiotopic. Where's diastereotopic? Take a look at the hydrogens in here. Okay. And that methylene, do the same process. If I make one of those an X, and the other one leave it alone, the relationship, whoa, went the other direction. The relationship now between those structures is they are diastereotopic, which means those hydrogens are unique from each other. Why does that become problematic? If you see a chiral atom, it's about to get real.